Well, good evening, everyone. It's Mrs. Suter, and we're back today with our after-school science. And this one today is called Balanced and Unbalanced Forces. And so today, what we're going to be needing for some materials is we're going to be needing a cup that's about half filled with water. Okay. We're going to be needing an index card or a piece of cardboard about this size, which is 5 by 7. And some quarters. Okay, I've got about 5 quarters here, but 3 or 4 will work just as well. You could use other coins, but quarters usually work the best because they're a little heavier. Okay, I also have a paper towel laid out on my table because sometimes things get wet and I like to wipe them off. Now, I'm going to set those things off to the side. If you need to gather your cup of water, your index card or piece of cardboard, and your quarters and paper towel, you may pause the video for a moment, go gather those materials, and then meet me back here. When you're ready, just hit the play button and you can go on with our lesson. Okay, so today we're going to talk about is this balanced and unbalanced forces. So we're going to talk about what a force is. So the word force, a force is simply a push or a pull. So anytime you push or pull something, you're using force. And that's exactly what the word means. It simply means a push or a pull. Now, when you have, I don't know if any of you have ever tried or seen the tablecloth trick being done, but this is done and is able to be done because of the understanding of physics, understanding of forces. So I'm going to show you this, and when you're watching, I want you to listen for the secrets. What is it that he shares with us that helps this to be able to be done? And then we're going to talk about the science behind it. Okay, so let's watch the video.
All right, so the first thing, we're going to whip the tablecloth off because every kid that's out there that's watching, and I know you are, and you're saying, I got to whip the tablecloth off because you've always wanted to. Here's the secret. The first thing is you need to go get fabric that does not have a hem. So if you see that right there, see how there's not a hem?
That little
right?
sewn edge
so that
is
little
gone.
frayed thing that's right there, that's
Yeah.
perfectly fine. That's what
That
we
thread
want.
I just pulled up, is that going to be a problem?
No, that's going to be fine.
Okay.
The second thing is this, is you're going to pull straight down to your toes. So on the side here, what it's going to look like is this, is you're going to hang on to it like this, and your hands are going to be here, and you're going to pull straight down like that.
Oh,
Hear that little whip?
Yeah, hear the whip.
That's good.
That's
all
the
right?
sound of success.
That's good. That is the sound of success. All right. So fire it up. Let me just hear a little whipping action.
All right,
We'll just see how good it is.
Look what I've done.
It's perfectly fine. Yeah, you're going to be great.
Okay.
So hands there, whip down, ready, set, nice. Now, second rule is this: you never use your own. Now you're not done yet. Get it back going. All right. None of the elbow thing just yet, because you're not there.
All right, okay.
All right, so now you never use your own dishes, right? You always use a friend's dishes. That's exactly right. All right, so here's what's going to happen. Let me put these together for you here like this. All right, so now it's the law of inertia, the tendency of an object to stay at rest until a force acts upon it. So gravity's pulling down this smooth cloth here, and the lack of an edge, hopefully it'll keep it in place. Ready? All right, so be a rock star. Grab the ends.
Me?
Do you think I'm doing it? All right. All right, straight down. Ready? 3, 2, 1, straight down. That was nice.
Thank you.
See, that was nice.
Thank you.
But see, most first graders can do that. So here, do that again. All right, so put it back up again, because I have another one for you that I thought might be kind of fun. All right, so here's what happens is you got it there. Yes, this is perfect. All right, so here we go. If we add mass, then that's probably a pretty good thing. So that's where these glasses going to come into play. So if you've ever seen somebody do it before, they sometimes will add something on top like this. Got that? And then we add a little bit of mass. All right, so here we go. So here's a little bit of mass. So how about a little bit here?
I'm on all evening.
You're going to be, and I think you're going to be good. Yeah, you're going to be just perfect at this. Isn't that great? Now, for a mere mortal, this would be good, but you are more than a mere mortal. So that's where this goes on top, and this guy is right up here like this. All right?
There's no way.
There's a strong possibility that this is not going to work. All right? But it's okay. We got to see your first one, and we'll cut all the rest out. All right?
Oh, gee.
Are you ready for this?
Is it me?
Yeah. Yeah, again, it's not me. All right? All right, so I'm going to move you down just a little tiny bit. I think you're going to be great.
Set me
all right?
up for success.
So you're going to be here like this.
All right.
Your hands are tight, straight down to your toes.
Okay.
Got it?
All right.
Straight down to your toes. No hesitation at all.
All right. Okay.
All right.
Miss
Ready?
Christensen is
little
ready
drum
to
roll.
exit the studio.
I'm gonna count you in. Ready? 3, 2, 1. Hard. And the crowd goes wild.
Thank you.
Now you can do your little thing here. Do your little thing here. Yes, that's perfect.
All right, so you could see that he did the experiment and it worked, but there was a few things that Steve Spangler told us that were secrets. One, make sure that the tablecloth does not have that sewn hem on the end, because if it does, it's going to catch those dishes in that gap, and that'll pull them off. So that's going to be a trick. Second, you want to make sure that there was notice how careful he was about making sure that everything was smooth. You don't want to have anything, any curves or wrinkles in the tablecloth, or it will not work. Third thing is his tablecloth, the fabric he used was very silky or smooth, because if you have things that have a lot of texture to them, that texture adds friction, and friction grabs a hold of, the texture grabs a hold of the dishes, and that causes them to come off. So there were some tricks to that. But what we're going to talk about is why was that trick able to be done? Okay, so why that it works is because of inertia and the energy. And when we balance forces, things stay still, they don't move. But when I unbalance forces, that's when we get motion. So we're going to do a little lab here on the computer and talk about forces, and then we're going to try an experiment very similar to what you saw Steve Spangler doing and showing us about, and I'm going to talk about how that works. Okay, so this is a lab from PhET Simulations. This is free online, so you're welcome to get on this at your free time. It's from PhET, P-H-E-T, PhET Simulations, and it's called Forces in Motion. It's basics on net force. Okay, so it's the game of tug of war, which is a great game to show us about forces. Now I'm going to turn on the sum of the forces and my values so that I can see what forces are being used. So these are my guys. Okay, this little guy right here, he's small, so he only has 50 newtons of force. He can't pull very hard. Okay. This guy right here, same size, same amount of force, 50 newtons. This guy right here, he's a little bigger, so he's got more force. He gets 100 newtons of force. And then this guy right here is bigger yet, so he can pull with 150 newtons of force. All right. Now, newtons is the way that we measure force. All right. And this force is moving in the direction of the left, and this is the strength of the force, 150 newtons. All right, same thing on this side. We've got 50 newtons of force, but this time it's going to the right. 50 newtons of force for him, 100 newtons of force for this middle guy, and 150 newtons of force for the taller guy. But this time the direction is opposite. So if I want to play the game, I need to figure out how much forces I need to put on each side so that we can tell how it'll move. So if I put this guy up here, he pulls to the left with 150 newtons. And then I pull this guy up and he pulls to the right with 100 newtons. You can see that this guy is going to be pulling with about 50 newtons more force. So since these forces are unbalanced, we should see movement. So in which direction? Should be to the left because there's more force going this direction. So when I hit go, you can see that my cart is slowly moving to the left because the blue team has more force. Okay, so we're going to reset, put my two forces up here. Now this time I'm going to try to balance my forces. So I'm going to move both of my guys up here. This one is pulling 150 newtons to the left. This one is pulling 150 newtons to the right. Since they're both pulling in opposite directions at the same force, I have a zero or a balanced force. So when I hit go, you can see that the cart does not move. So when my forces are balanced, no movement takes place. When I unbalance my forces, then I have motion. So now I'm going to put this guy up here. Now I have 200 newtons of force on the red team and 150 newtons of force on the blue team. So now I see that I have 50 more newtons of force going to the right, and that allows the cart to slowly move and make the red team win. Now, if I don't want the red team to win, if I want it to stay balanced, I have to make sure my forces are balanced. So I'm going to change and I'm going to say, well, let's put this guy. And then I'm going to put this guy. And then over here, I'm going to put this guy. Now, even though there are two people over here and only one person over here, the forces are still the same, or they're balanced. So 150 newtons to the left and 150 newtons to the right, we have balanced forces. So when I press this, I should have no movement or standing still. Okay, now if I add another guy, now I have unbalanced forces. I have 50 more newtons to the right, and that will make my cart move to the right. So unbalanced forces cause motion. Unbalanced forces cause things to sit still. All right, so let's see, I'm going to put this guy and this guy and this guy. Now, how can I do the same thing over here with just two people? So I know that this one is 100, 150, 200 newtons to the left. So if I want 200 newtons over here, I'm going to say 150, 200, and now I can see the balanced forces, no movement. Okay? If I unbalance the forces and give this guy 50 more, he's at 250, and then the cart will move. Okay? All right, so this is a simulation that you can play around with on your own. And like I said, it's PHET, P-H-E-T, simulations, and this one is called Forces in Motion, Basics Net Force. Okay? Now, force, as we said, is a push or a pull. Now, when we apply force to some things, it can make an object move. It can actually make an object slow down, stop, or change directions. So gravity is an example of a force that you cannot see. It's invisible, but it's there. And we feel that force on us because we have to actually apply force to lift our foot off of the ground. Now, this little girl jumping on the trampoline here, she is using two forces. You have the force of gravity, which is pulling her down, and then the force of the trampoline pushing her back up. Now, when she's flying in the air, we know the force of the trampoline was pushing up, and that allowed her to go up to escape gravity. But gravity keeps pulling her back down. So gravity is constantly pulling on her, and the trampoline is only acting on her when she touches it. So that is why she is bouncing. Okay? Now, when you're riding your bicycle, there are all kinds of forces in play here. And these forces, obviously, our goal is to unbalance them so we get motion. So you have your force, the force of your foot pushing on the pedals. That's one of your unbalancing forces. Okay? The second force you have is the push and pull of your hands on the handlebar. That causes the direction. Okay? And then you also have the force of gravity holding your bike down. And then there's the force of your tires rubbing against the pavement, and that's force is friction. So you have lots of forces in action when you're riding your bike. Okay? Now, soccer also has a lot of forces in play. So, and if you're a good soccer player, you have to know exactly how to manage your forces. Since force has something to do with the strength and the direction that the ball is going to travel, you have to know exactly how much force and in what direction you want the ball to travel to get it to go to your player. So let's say you want to pass the ball to another player, and that person is very close to you, and he's off to the right. You have to know that you need a little bit of force so that you're not kicking the ball past your player, and you know that you need to kick it in the direction the force needs to come from the left to push it to the right. So as a good soccer player, you have to know exactly what direction and exactly what strength you need to kick the ball. If your teammate is far down the field and he is in front of you, You need to know that you have to apply a lot of force to the back of the ball to get it to move forward at the strength that you need it to reach your player. And that's just like rocket scientists. Rocket scientists have to be very careful about how much force they give the rocket and in what direction that force is in. Even a very small mistake will get the rocket off course, and then the mission will not be successful. So strength and direction of your force is really important. Okay, so just like in the tug of war we talked about before, when our forces were balanced, there was no movement. But as soon as we put more force on the left or the right, we got motion. And you could see that the cart moved, just like here where you move the people. Okay? Just like if you're playing a game of tug of war with your dog and you have that pull toy and he has one end and you have the other. When you're both pulling at the same strength in opposite directions, both you and the dog are going to stay still. But if you were to let go of that rope and suddenly your force became more from the dog, then the dog's going to fly backwards because that's the direction of the fall or of the force, and you are unbalancing the forces. Okay, and so if one of you were to let go of the chew toy, the other person would then fall backwards because of the unbalanced force. Okay, so when forces are balanced, there's no motion. So right here, I have the force of gravity pulling the ball down to the ground, and the force of the ground pushing back up on the ball to hold it up. So since these forces are acting in opposite directions at the same strength, this ball will stay still, no movement. Okay. Now, let's talk about that with our experiment. All right, so now let's go ahead and get out our cup of water. Okay, so I'm going to push this down so you can see. Got my cup of water. I've got my quarters, my paper towel, and my index card. All right, now I'm going to start off by putting my cup of water down. And you can see that the cup is balanced, it's not moving. I have the force of gravity pushing down on the cup to hold it down, and the force of my desk pushing it up at the exact balance force. So this cup is not moving. Okay, now I'm going to add the card, my cardstock. Now I have balanced forces again. So the cup is pushing up on the cardstock or my index card, and gravity is pushing down. The strength is equal in opposite directions, so my card is sitting still. Now, I'm going to take my quarters, and I'm going to do the same thing. So now I have the force of the card pushing up, the force of gravity pushing down. So we have talked a little bit about inertia. Inertia is one of Newton's laws, first law of motion, which says an object at rest wants to stay at rest. And right now my quarters are resting, and they will stay resting, and my card and my cup, unless I put a force on it. So what I'm going to do is I'm going to put a force on the card. When I put a force on the card, it is going to unbalance the card and create movement. Now, when I remove this card, I am unbalancing the forces of the quarters because right now they're balanced between the card and gravity. So if I take my card and I quickly move it off to the side, my quarters wanted to stay at rest, and so they fell straight down into the cup because my forces were unbalanced. I removed the upward force from the card, and that made my quarters fall down because then gravity had more force than the card. All right, so they're just like the quarter, or just like the tablecloth trick, there's a couple tricks to this as well. One, you want to make sure that your quarters are dry when you do this, because if you get your card wet, it adds friction, and friction is a force and it can unbalance things. Okay, so I want to make sure my card is also heavy enough that it can actually support my quarters. All right, then I want to make sure that when I add the force, I am adding it directly to one side or the other. So I'm moving things to my right And so, because that's the hand that I work the best with, and I'm pulling straight to the right to create that, and then that causes my quarters to fall straight down. If I bend my card up or down, it's going to add more different direction to my force, and my quarters may not end up in my cup. So I have to be careful when I'm doing this. So I'm going to take it quickly, and you can see they fell straight down into the cup. All right, so you guys can do that one, and you can try adding more and more coins to see how much you can get to fall into your cup. All right, so that's one. It's kind of like our tablecloth trick. Now I'm going to put my cup of water and my index card to the side. I'm going to keep my quarters out because I have a couple more things that I can do with my quarters. And these are some more tricks that you can do and show people and challenge them to work with their force as well. Okay. Now another one, and this is actually a game that people all over the world play. It's called coin snatching, is what it's called. Okay, now I'm going to tell you I'm not very good at it, but I will show you a video later of someone who is very good at it. Okay, so I'm going to start very easy and just start with 1/4. Okay, I'm going to take my hand and put it up here behind my neck like this, and then I'm going to put the quarter on my elbow and balance it. Now right now the quarter's not moving because my forces are balanced. My elbow's holding it up and gravity's pulling it down. Now when I move my elbow, the quarter wants to stay in motion. It's going to begin to fall down. But because I can put more force on my arm, I can try to catch this quarter in the air before it hits the ground. Okay, and it's called coin snatching. And I'm going to tell you I'm not very good at it. So you go to quickly, oh, and then I caught it. Okay, so you can put your quarter here. You're going to balance it, add your weight, and catch the quarter. You can see that time I didn't catch it. Now, if you can do 1/4 consistently, then try 2. Put 2 quarters up there. Now remember, you have to balance them. You have to figure out exactly how much force you need to catch the quarters. And you can see I haven't practiced very much, so I'm not as good at it. Now, I will show you a video later of someone who is good at this, and this is a world game, and the world record for coin snatching is 628 coins. Now, first of all, I can't even imagine stacking 628 coins on my elbow, let alone trying to catch 628 coins. All right, so those are some things that you can play around with force. Now, the next thing we're going to talk about is another challenge that you can do outside your house. And you can use like a basketball and a tennis ball and a golf ball. And I will show you a video of that here in a little while. But what I'm going to do is show you a similar kind of thing. And I'm using a modeling tool called Seismic Accelerator. You can get it from Amazon. I think it was like 20 bucks. But it also comes with goggles, because when you are playing with things that fly around, you want to protect your eyes. Okay, now this allows me to multiply my force. Okay, so right now I have this little red kind of bouncy ball. When I drop it from here, you can see that it bounced, but it won't get back up to the height that it was. So when I first bounce the ball, I'm going to put my roller here. When I first bounce the ball, I'm going to bounce it from the 5. When I get it back up, it only came back up here to about 2.5. So it lost about half of its energy. So right now it has potential energy holding it. When I let go, it becomes kinetic. And then when it hits the table, there's some friction of the table and the ball, which takes away some of that energy. And then when it bounced back up, it only went about half its height. Now, I can make the height of this ball much bigger by adding more force to it. Okay, so I'm going to multiply the force. On this particular device, I have 3 rubber balls. Now they are stuck on here. They're not going to come off, but they can move. And so what I do is I take this little ball and I put it on top. And the reason the stick is here is to keep everything nice and balanced. Now, when I drop this ball, the force of this ball is going to transfer into this one, multiply it, it's going to go and transfer into this one, multiply it, and then that's going to all be transferred to this one, which then can get the force of all of them. Okay, so when I drop it on the ground, the red ball is going to fly off, and it's going to reach a much greater height. So I'm going to show you that I can actually get this to hit the ceiling. And you can see that the ball bounces a lot higher when I add in the force of these other balls. So I'm not going to drop it high enough to hit the ceiling, because you have to drop it from a good height, and then I can make it hit the ceiling of my room. But I'm not going to do that because I'm, oh, but you do have to keep everything balanced. So, woo, there, got the ceiling that time. All right, so when we add the forces, when we multiply those forces, it makes it so that this ball gets all those forces. So you're going to see a video of this here in just a minute, using a basketball, a tennis ball, and a golf ball. Okay, but if you want to play around with the seismic accelerator, this is what it looks like. All right, so now I'm going to show you that video of the basketball trick, and then you can practice that at home. Okay, so let's go here. Let me see, I'm not sure if I have this shared, so I'm going to, okay, pull that up here. And here's the video of that. Oh, sorry. Back it up here.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm gonna try the golf ball on top of the bouncy ball, on top of the basketball. And then I'm gonna explain how it's related to a supernova. Did you see that? Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
All right, so as you can see there, just like I showed you with the seismic accelerator, when you bounce those balls one on top of the other, that multiplies the force, and that creates that top ball to get the force from all of the ones underneath of it, that energy that transfers between each one, and then that causes the top ball to fly much higher than it would without the energy from the ones transferred below it. So that is our lesson on force today. I hope that you learned a little bit about balanced and unbalanced forces. That balanced forces make things stay still, not moving, and unbalanced forces cause motion. So play around with your quarter experiment, your snatch quarter, and your cup and quarter experiment. Try to challenge someone in your house to do those games as well. Until next week, we're going to learn about waves. I will catch you next Tuesday, 5:30 to 6:30. Until then, keep wondering.